Dear student, welcome back to my channel Whiteboard e-learning. And in my previous video, we have started the topic that is heating effect of electric current. This one you can see 14.2 heating effect of electric current. And you can see the applications of heating effect of electric current. We have given example that is heater, this one, the heating element. And next example or application what I have told you, that is the electric incandescent bulb. This is the second example, and third applications of this one is fuse. Today we will start from this topic. We will focus on this. Let us study this first.
If a large current passes through a wire, the wire may become so hot that it may even melt and break. But is it possible for a wire to melt and break? Let us check it out.
It will be possible. So I will show you one activity. Activity is 14.4. So let us read the topic.
Make the circuit we used for activity 14.3 again.
Okay, so this activity 14.3 will show you the activity, previous activity 14.3. That figure we will take here. You can see, instead of taking one single cell here, we will take 4 cells, and instead of taking nichrome wire, we will take now steel wool. So now read it.
However, replace the cell with a battery of 4 cells. Also, in place of the nichrome wire, tie a thin strand of steel wool. The steel wool is commonly used for cleaning utensils and is available in grocery shops. If there are any fans in the room, switch them off. Now pass the current through the circuit for some time. Observe the strand of steel wool carefully. Note what happens. Does the strand of steel wool melt and break? Wires made from some special materials melt quickly and break when large electric currents are passed through them. These wires are used for making electric fuses. Fig. 14.14.
And now in all buildings, fuses are inserted in all electrical circuits. There is a maximum limit on the current which can safely flow through a circuit. If by accident the current exceeds this safe limit, the wires may become overheated and may cause fire. If a proper fuse is there in the circuit, it will blow off and break the circuit. A fuse is thus a safety device which prevents damages to electrical circuits and possible fires. So we will make you understand how it works. Actually, you can see one general fuse, the old type of fuse is here, and in between the two erected metal strips, one wire has been connected, and that will act as a fuse. How it works? Actually, when current flows through it, depending on the load in our room, we have selected a particular fuse. Amount of current exceeds through this wire, then it melts. How it melts? Actually, current flows in the wire. You know, when current flows through it, it will be heated up. So such type of material we have chosen here, it quickly attains that temperature and melts down. When it melts down, automatically this will be disconnected, and in this way we can prevent such type of damages or any hazards. So this is nothing but a fuse. Fuse is a safety device. When the current exceeds the specified limit, then it melts down due to the heating effect of electric current, and just it breaks the circuit.
Fuses of different kinds are used for different purposes. Fig. 14.14 shows fuses used in our houses. Fuses shown in Fig. 14.15 are generally used in electrical appliances. We observed the heating effect of the electric current and learned how we use it to our advantage. Does the electric current have other effects also?
We have understood electric current has one particular effect, that is the heating effect of electric current. Generally this is undesirable, but we have made this undesirable effect in our life which is very useful. That is, we have used heater, we have used incandescent lamp, we have used such type of fuse. But you know, these are very old type of mechanism and devices. So these devices has been updated, and now the instead of fuse we are using this one. This is actually called MCB. The full form is that miniature circuit breaker. It does not works. The working principle of MCBs are not heating effect of electric current. It is more useful than the fuse and more efficient. This works with a different mechanism that depends on the electronics.
These days miniature circuit breakers, MCBs, are increasingly being used in place of fuses. These are switches which automatically turn off when current in a circuit exceeds the safe limit. You turn them on and the circuit is once again complete. Look for ISI mark on MCBs also.
Next topic, does the electric current have other effects also? Yes, this effect we know, that is the magnetic effect of electric current. So activity 14.5 we will just read.
Take the cardboard tray from inside a discarded matchbox. Wrap an electric wire a few times around the cardboard tray. Place a small compass needle inside it. Now connect the free ends of this wire to an electric cell through a switch as shown in Fig. 14.17. Note the direction in which the compass needle is pointing. Bring a bar magnet near the compass needle. Observe what happens. Now, while watching the compass needle carefully, move the switch to the on position.
We have wrapped the wire in a spiral binding type, and you can see here in between these we have placed one compass needle. Compass needle is nothing but a small magnet, very tiny magnet is pivoted in this glass case. You know that magnet always align itself in a particular direction, that is the north south direction. So you can see it will obviously in that position. So if you just bring one magnet, bring one normal bar magnet or any type of magnet, then you will see it will be deflected. The direction of the north south direction of this compass needle will be changed. So when the compass needle direction will be changed, if we bring one magnet, okay, I think you have understood that. But now instead of bringing one magnet, we have just switched on this circuit, and again that time we have seen a interesting effect. Again the compass needle has been deflected in a particular direction, though there is no magnet we have brought. So what is happening here? So now read it.
Note the direction in which the compass needle is pointing. Bring a bar magnet near the compass needle. Observe what happens. Now, while watching the compass needle carefully, move the switch to the on position. What do you observe? Does the compass needle deflect? Move the switch back to the off position. Does the compass needle come back to its initial position? Repeat the experiment a few times. What does this experiment indicate? We know that the needle of a compass is a tiny magnet.
So what is happening here? So if we just bring one bar magnet, obviously due to the interaction in between the bar magnet, it will be deflected. It is very common. But instead of bringing such type of bar magnet or any other magnet externally, just we have switched the circuit on, and then we have seen the same effect has been occurred. That means the conclusion is that current carrying conductor, yes, this one the current carrying conductor. So current carrying conductor behaves as a magnet. In the first thing what we have taken a real magnet. Okay, that is actual magnet we have taken. So instead of taking actual magnet, if we just switch it on, then we have seen the same effect we got, same effect we have observed. That means electric current carrying conductor behaves as a magnet. So that magnet we cannot see, that magnet we cannot observe, but is a virtual magnet. So this thing has been discovered by Hans Christian Ørsted, and that is a great discovery. So we'll read that discovery here.
Points in north-south direction. When we bring a magnet close to it, the needle gets deflected. We have also seen that compass needle gets deflected when the current flows in a nearby wire. Can you connect the two observations? When the current flows through a wire, does the wire behave like a magnet? This is what a scientist called Hans Christian Ørsted, Fig 14.18, also wondered. He was the first person who noticed the deflection of compass needle every time the current was passed through the wire. So, when electric current passes through a wire, it behaves like a magnet. Magnetic effect of the electric current. In fact, an electric current can be used to make magnets. Do you find it too surprising? Let us try it out.
And another example activity is there. You can see, just connect this wire with a switch and cell, and we have wrapped the wire in a spiral mode throughout the nail, and then we have switched it on. You can see, few minutes ago I have told you, when electric current passes through a wire, it behaves like a magnet. So actually this nail will behave like a magnet. If you just bring some small nails of iron, so that will be attracted, so interaction will be there. You know, magnet attracts magnetic materials. Magnetic materials means it is made up of iron, cobalt or nickel. So it is confirmed that current carrying conductor behaves as a magnet. This type of magnet is called actually electromagnet. You have already read about this electromagnet in the previous classes, and you know this electromagnet has some particular property. We can just increase the electromagnet strength, just increasing the current in the circuit, and also decrease by decreasing the current. Have a look on this electric bell, which is actually the applications of magnetic effect of electric current. Actually in our school you have seen such type of bell. After each and every period this rings, and what is the mechanism of this electric bell, we'll just show you. To understand the mechanism of this electric bell, we'll just read this topic.
We are quite familiar with an electric bell. It has an electromagnet in it. Let us see how it works. Fig. 14.20 shows the circuit of an electric bell. It consists of a coil of wire wound on an iron piece. The coil acts as an electromagnet. An iron strip with a hammer at one end is kept close to the electromagnet. There is a contact screw near the iron strip. When the iron strip is in contact with the screw, the current flows through the coil, which becomes an electromagnet. There is a contact screw near the iron strip. When the iron strip is in contact with the screw, the current flows through the coil, which becomes an electromagnet. It, then, pulls the iron strip. In the process, the hammer at the end of the strip strikes the gong of the bell to produce a sound. However, when the electromagnet pulls the iron strip, it also breaks the circuit. The current through the coil stops flowing. Will the coil remain an electromagnet?
So you can see here one hammer is there. So this hammer end is connected with the iron strip, and from the iron strip one wire is coming, and this wire is wounded over a iron cylinder, and the end of this wire is again wounded over a second iron cylinder, and it comes from that, and it is flowing, comes to this battery, and then comes to here to complete the circuit through a screw. And you can see here one spring, it is not shown in the figure. One spring is also there. One spring. This spring is connected. This spring is connected with this iron strip and one arrangement here that will be connected in between this arrangement and this iron strip. So what will happen when the circuit is complete? So you can see current will flow in this circuit. So these irons will be, these wires and iron core will act as a electromagnet. So when it will be electromagnet, So magnetic material, this is nothing but a iron strip which is made of iron, will be attracted towards these windings. Then the hammer will hit the gong, and again when the hammer will hit the gong, distance from the screw will be greater and it will be detached. When it will be detached, you can see current will not flow, that is from the closed circuit it will be open circuit. So when it will be open circuit, current will not flow, so ultimately the electromagnet will no longer work. So when electromagnet will no longer work, then it will not attract the iron strip towards this winding. So few minutes ago I have told you there is a spring, so due to this spring it will be pulled in this direction. This type of pulling,
the hammer
will come back to the previous position, but when it will come back to the previous position, again it will be attached, the connection will be again made. So when again the connection will be made, the circuit is here again closed circuit, then again the electromagnet will work and again it will be attracted, then again disconnected. So in this way the electromagnet will activated and then deactivated, electromagnet will activated and then the next moment it will be deactivated. In this way this hammer will hit the gong in a repetitive way, and that is nothing but the ringing of bells. I think you have understood this topic. So thank you for watching my video. If you think video is helpful to you, don't forget to hit the like button and subscribe my channel for next upcoming videos.